Okay, a bit more stats for further maths. This is exercise 8C, looking at what are called unbiased estimators of the mean and variance. And unbiased basically means the best possible estimate that statisticians believe they can make for the mean and the variance of a population. Remember, of course, that when we look at the population, if we was able to, go and find out the average height, for instance, of a variety of different plants, if we measured every single plant in the world, then we'd know exactly what the mean was. But of course, that's impossible. There's a variety of situations where it's impossible to measure an entire population. And so therefore, we end up doing what's called a sample. And that sample produces estimates of the mean and the variance. And there are reasons why sometimes people want to do a better estimate of the mean and the variance, and those are called the unbiased estimates. So it's this word unbiased which kind of implies it's a fair and unbiased estimate of what we're trying to find, this mean and this variance. Well, let's have a go at looking at it anyway. This is what it says in the formula book for further maths. On page 6, it basically says unbiased estimates of the population mean. Notice it describes it as the population mean and variance, and it says unbiased estimates of it are given by these. So this is a formula we've seen before. This is what we've seen before. And this certainly isn't what we've seen before. This is new. And so it implies that at least one of them, this is, by the way, the mean, and this is meant to be the variance formula that we're meant to use if they ever say find the unbiased estimate. So again, remember that these things, this is the symbol we usually use, by the way, for the mean of the population. And sigma squared, lowercase sigma squared, is what we usually use for the variance of the population. And as I've highlighted, in reality it's impossible to find, so we do a sample, and these are the symbols. Notice it's a different symbol for the mean. This is called the sample mean. This is called the sample variance, and again we do tend to use this sigma again for the sample variance, sometimes written sigma x down there like that. Those are the formulas we've seen before. That's no shock to you. What's new then is that the unbiased estimator of the mean and the variance, they have their own symbols actually. This is the unbiased estimator. Well, I say it is. Interesting, in the formula book, they don't bother giving you a symbol. They just say the unbiased estimate is. But notice it's pretty similar in its structure to that. Whereas for the unbiased estimate of the variance, we actually use s squared. We will do in class, as opposed to lowercase sigma squared. What are the formulas? Well, you've just seen them. This is the unbiased estimate of the mean. It's actually identical to x bar. This is no different. So I'm going to write here the same as x bar. It's no different. This is the unbiased estimate of the variance. Notice we first start, we're using s now, capital S. But notice this is not the same. This is the new bit. Before we had sigma squared equals sigma x squared over n minus x bar squared. Notice effectively that has now had this bit chucked in the front of it. And that's the difference, the main difference between what we would normally do and what we're going to do today. So really we're saying the unbiased estimate of the mean is the same as we've always used, same formula. But for the only one that really matters for is the variance. The variance is different. So let's come back to that now. Here's a question. It says a student wishes to estimate the mean and the variance of the playing time in minutes of CDs sold in the UK. She took a random sample of 9 CDs as follows. Now we've got these 9 numbers then, and it says use the formulae with the student's data to find unbiased estimates. So whenever it says unbiased estimates, that's what we're going to do. So let's just do it now. Just chucking this up here. X bar, the unbiased estimate, is simply all these added together. So that can't be hard to do. I've been kind to you, by the way. I have already worked out what sigma x squared is. If I was really kind, I would have worked out what sigma x is as well. But I'm just going to quickly type those in. 49 plus 56 plus 55 plus 51 plus 57 plus 61 plus 52 plus 63. And I get 522. I don't know if that's right. We'll see when I do it in a bit. So anyway, it's 522. How many were there? 9 divided by 9. Divided by 9 equals, and it's 58. So it looks right, just in the fact I've got a nice answer. I suspect I deliberately did that. Now notice then this s squared. This is different. So because there's 9, this is my n. So it's 9 over n minus 1 is 8. Times by whatever I normally do. And I normally go this sigma x squared, which luckily I've calculated already, 30,550, divided by 9, minus this answer squared. So I reckon I should be able to do that. So what have I got? 9 divided by 8 times by, I should turn that calculator on first. And I'm just typing it in now. And according to me, that's 34.25. Don't know if that's right. Of course, we can chuck this into our calculator and just type the numbers in, and it should tell us. So it's worth doing. Now, I'm actually using, rather than the graphical calculator, I'm using the Casio calculator now. So that's one I've got. So I'm just going to use that calculator instead. I'm going to go to Menu and 6, and it's one var statistics again, one variable. And I just type these numbers in. I could have done this right at the beginning, I suppose, but I didn't. Try to do this properly. So I'm just typing those into my frequency table on my calculator. If you're using the graphical calculator, you put them in list 1. And having put those in, I can press Option on the calculator, one variable statistics, and it just tells me. And the important thing I want you to look out for is your calculator says, well, my calculator, this calculator says s squared x. It also says sx, so depending on what calculator you're using. I think the graphical calculator will probably only give you this one, 5.852 it says. But this Casio Class Whiz does a bit more. It actually tells me the variance. It says 34.25. At least I found it, and I've got them right. So answers 34. Look at that, I rounded. I don't know why I rounded. It's 34.25 sounds better to me because it's an exact answer. 58 is right there. I've got some fish. These are meant to be fish in some kind of packing tray, it sounds like. The masses in pounds of a type of fish caught in the North Sea are known to be normally distributed. 200 such fish were caught and the masses were recorded. The summary statistics are below. Okay. And all it wants are unbiased estimators. The fact it's normally distributed doesn't really matter. All I want to know is this says this information. How many fish? It was 200 fish. Okay, let's use our formula. So the formula for x bar, the unbiased estimator, of course, is this sigma x over m. So let's use that formula. It's 626.5. I'm dividing by n, which is 200. If I do that, 626.5 divided by 200 equals, I'll try that again, and it comes up with 3.1325. So I'm just going to, I'll write it all, but I'll round it in a bit. I'm going to use that number in a bit, so that's why it's probably worth our while keeping it. S squared, our unbiased estimate of the variance is, well, we've seen it's n over n minus 1. So that's by sigma x squared over n minus x bar squared. Well, technically this square, but it's the same thing. So it's 200 over 199. Now one thing I would point out is 200 divided by 199 is almost identically equal to 1. And it's because we've got a very big sample, it doesn't make much difference to my answer. Unlike if I only got a sample of 5, you can imagine if I had a sample size 5, then n over n minus 1 becomes 5 over 4. And what this thing does, you see, is it increases the size of the variance. And it's believed to be the case that, and probably proven to be the case, that this is a better estimate of how spread out the numbers are. And you can see with small sample sizes, here I'm timesing by 1.25. If n was equal to 3, n over n minus 1 would be 3 over 2, which is 1.5. You can see the smaller the sample size, the bigger the amount I'm timesing my calculation by. 1.5 is massive. You can, if you just do on your calculator 200 divided by 199, I get 1.005. It's almost not worth bothering with because it's such a big sample. But I'll do it anyway. It's 3220.1875 divided by 200 minus 3.1325 squared. So let's do that on my calculator. Times by. I'm just typing it in. Minus the 3.1325 squared, close bracket, equals, I get 6.3-ish. Let's see what exactly it is. 6.32 to 366. So now I'm quite happy to call that 3.13. Now I know my actual answer. What were the answers? 3.1325. Interesting, I wrote it all, and then 6.32. So I agree with those. The third example. This is, I think I took this from the textbook. An examination board has developed a new syllabus and wants to know if the question paper is of the right length. A random sample of 50 candidates, so n is 50 obviously, was given a pretest on the dummy paper. Oh, they've given this here. There's sigma t and the sigma t squared. Okay, so it's easy enough. So t bar, my unbiased estimate, is simply 4050 divided by 50. That's easy enough. 4050 divided by 50, 81. Okay, sounds right. And then my S squared, my unbiased estimate, is 50 divided by 49 times by this 329800 divided by 50 minus my 81, which I just calculated, squared. So you can see this is pretty easy to do. 50 divided by 49 times by that bracket 329800 divided by 50 minus 81 squared, close bracket, equals, and I get 250 divided by 7, or 35.7. That's my variance. I don't know that. 81, 35.7. Doesn't tell me how to round it, so 366 sounds best for me. And that's it. It's just getting used to this new formula. We will be expected to know this formula. Now, and what also happens is there are questions coming up on the hypothesis test which require us to use the unbiased estimate rather than the normal standard estimate, if you like. And just remember this idea again. I'll just remind you of it one time. S squared, remember, is n over n minus 1 sigma x squared over n minus x bar squared. And it highlights how the bigger the sample you make, the more likely your answers are to be an accurate description of what you're hoping to find out, what an accurate description of what the population variance is likely to be. So notice this then, a reminder, if n is a big number, like 1,000, if n is 1,000, then n over n minus 1 is 1,000 divided by 999, and that's practically equal to 1. That's not really changing. 1,000 divided by 999, it's 1.001. So almost no difference to times them by just nothing at all, just by 1. But n equals to 4. Well, n over n minus 1 is 4/3, which is 1.33. You can see this would increase the variance quite a lot. This is emphasizing the spread of the data more for small samples than for big samples. Big samples are almost insignificant, barely worth bothering with. With little samples, it makes a big difference. And it highlights to any statistician that you should increase the size of your sample as much as possible, as long as it's possible to do it. Big samples are better than small samples. So anyway, we're going to do those questions in class. Best of luck.